Hello and welcome to another video lesson with Takoa Lawson. Today we're going to be looking at some example problems for the circular motion unit. Here we're looking at that same ball that we were whirling before on our string. However, it was an isolated system. So it was only the ball on the string. There were no other forces acting on it. However, we're now on a ball on a string and we're rotating in a vertical circle. The previous problem, this is essentially the same as the Ferris wheel. It's just instead of the Ferris wheel structure, or you standing on a floor or sitting in a seat where it's the normal force pushing up, it's actually going to be the force of tension that's pushing you up in this case. Here, when we first start drawing our free body diagram, it's actually going to look the same as the isolated ball. We know that there's a force of tension at that point acting on it. However, since we're not in an isolated system, we're near Earth, and it's a vertical circle, so that means the Earth is down here. There has to be a force downward, a force of gravity. However, since there's going in a circle and the center of the circle is up, there has to be a net force towards the center. So the force of gravity can't be greater than the force of tension. It can't even be equal to the force of tension. It has to be less than the force of tension to be able to make our net force towards the center. That's different than if we were at the top. If we were at the top and we were drawing a free body diagram, the force of gravity would be going down and the force of tension would be going down. In fact, at the top of the circle, we don't have any forces going out of the circle. Now that we have a free body diagram for the bottom and the top, we can look at the two situations when we're trying to figure out where will the tension be the maximum. Looking at the top situation first, the net force, which is the centripetal force, has to equal mass times v squared divided by r. In this case, since all the forces are in the same direction, I'm going to make down the positive. That way I don't have to make the net force negative and each of these negative. The net force, which is downward in the positive direction, is going to equal the two other forces, which is the force of tension plus the force of gravity, because they're in the same direction. And that means the force of tension at the top of the loop is going to equal mv squared over r minus mg. Now if I look at the bottom, I do pretty much the same thing, and hopefully you're starting to see some of the repetition here. At the bottom, we're still going in a circle. We still have to have a net force towards the center of the circle. I'm going to make going up positive in this case, because I know the net force has to be up, and that's in the positive direction. Generally, since I can choose, I didn't in that last problem on the Ferris wheel, I made up positive. However, I should have made towards the center of the circle positive. That means that net force, or the centripetal force, is going to equal mv squared over r, and that's going to equal the positive force, which is the force of tension, plus the negative force, or minus the force of gravity. Again, I'm trying to get force of tension by itself, so I add mg to both sides. So we see at the top, it was mv squared over r minus mg. At the bottom, it's going to be mv squared over r plus mg. Notice these are constants. M's constant, V's constant, R's constant, G's constant, because we're moving around at a constant speed. mv squared over r minus mg, mv squared over r plus mg. Clearly, if you're subtracting a value versus adding a value, you're going to get a smaller value. So at the top, where tension has help from gravity, it's going to be the minimum. At the bottom, where tension is working against gravity, it's going to be a maximum, since gravity is a constant in both cases. It works out that the force of tension at the bottom is where we get a maximum. For the second part of the problem, which is what is the minimum speed the ball can have at the top in the loop in terms of g and r, at the top of the loop, the force of gravity and the force of tension are both going towards the center. Now the problem is, if you go too slow, tension will go to zero. If it goes to zero, you're at that minimum speed, because force of gravity is constant. You can only travel at one speed with the force of gravity to follow the loop at that radius. If you go slower than that, gravity will continue pulling. Gravity's not going to slow down if you need a smaller net force towards the center. Since gravity stays constant, it's not willing to reduce past whatever value it is. If you need a smaller force to stay going in the circle, gravity is going to be that greater force. It's just going to pull you out of the circle, and you'll just go into free fall. You'll just fall straight down. If you were in a roller coaster on the inside track of a loop-to-loop, then you have a V-min and you'd fall down. What we're really saying is that net force, which again I'm going to make towards the center of the circle, the positive direction, which is the centripetal force, which is mv squared over r, is going to equal the force of tension plus the force of gravity. But again, we're worried that if you slow down, tension gets smaller and smaller, because as I need a smaller force, tension can change. Force of gravity is constant, so we can't decrease, but force of tension can decrease, and that's how we get a smaller net force. Eventually, we're going to reach the point where the rope goes slack, or right at the point where the rope will go slack, where the force of tension goes to 0. At that point, mv squared, where this is v min over r, is going to equal mg. Again, m's cancel out. Oh, this looks very familiar. This is going to be that v min equals the square root of rg. Pretty much the same as Vmax. Vmax is the square root of Rg. The difference is if you're on the inside of the loop, it's a minimum speed because you'll fall on your head. If you're on the outside of the loop, it's a maximum speed because you'll launch off of the curve and become a projectile. That's really how you can tell at the top whether you're at a Vmin or Vmax. Here we see that car driving over a hill. A car driving over a hill is basically the same thing as traveling on the outside of the loop. It's kind of like being on that Ferris wheel. We're drawing a free body diagram of the car at the top of the hill. At the top of the hill, there's the force of gravity going down because it's constant. And then because it's touching the road, there's a normal force pointing up. The curvature is downward. So that means the net force has to be down towards the center, which means the normal force has to be less than the force of gravity. Otherwise, we wouldn't have a net force towards the center. The second question is express the maximum express the maximum safe speed the driver can go over the hill without going airborne in terms of R and G. We can go through the whole solution of F net equals mv squared over r towards the center of the circle is equal positive, so mg minus fn goes to 0. Vmin or Vmax, in this case it's Vmax, is going to be equal to the square root of rg. For our last problem, we're going to look at a situation where we have a ball on a string where it's still near Earth, but it's a horizontal circle, not a vertical circle. So we look at a free body diagram for this ball. We've got a force of tension acting at an angle relative to the vertical theta, shown in our diagram, and along a rope of length L. And then, of course, we've got the force of gravity acting downward. We're going in a circle. We're not moving up or down. We're going in a horizontal circle. So that means the vertical forces have to cancel out. Force of gravity has to cancel out with the vertical force, the force of tension. However, the horizontal forces can't cancel out. We still have to have a net force towards the center. In this case, since I have a force at an angle, I'm actually going to do the sum of the forces in the x and the sum of the forces in the y. F net in the y, or the vertical forces, is going to be mass times acceleration of the y, which is 0 newtons. The vertical force is going to be the force of tension in the y direction, positive, minus the force of gravity, or plus the negative of the force of gravity. This theta is between the vertical. This theta is between the vertical. So the force of tension in the y direction is actually going to be the force of tension times cosine theta. So that means when we add mg to both sides, Fty, since y is this side right here of this right triangle, that's the adjacent side to this angle theta, that means Fty is Ft cosine theta, add mg to both sides, is equal to mg. When we start looking at the x direction, F net in the x direction has to equal the centripetal force, because we're going in a circle horizontally, which has to equal mv squared over r, and ft in the x direction is only horizontal force, or ftx. Now, fty was ft cosine theta, then ftx must be ft sine theta. Using the horizontal forces is that mv squared over r is equal to ft sine theta. Now, between these two functions, I've got some extra stuff. I see here I have an r. There is no r in the diagram. They don't say I can use r. They give me L. I see a theta, which is okay. Sine, no big deal. I see this v, that's the speed, that's what I want to, but I have an m, that's a problem. I'm not supposed to have an m. And I have an ft, that's a problem. I'm not supposed to have an ft. So one of the tricks here is when I'm trying to get rid of the ft, I'm actually going to take this. I could do it on either case and solve for it, but I'm going to go ahead and solve for the vertical. You'll see why in a second. ft is equal to mg divided by cosine theta. Oh, so ft is mg divided by cosine theta. That means over here where I have ft, that's mg divided by cosine theta. So since ft is mg divided by cosine theta, I'm going to substitute that in. mv squared over r is equal to mg divided by cosine theta, that was ft, times sine of theta. A couple nice things happen. This m is the same as that m. I'm only multiplying and dividing, no addition or subtraction, so they can cancel out. So I have v squared over r equals g sine theta divided by cosine theta. Sine divided by cosine is actually opposite divided by adjacent, because the hypotenuse ends up canceling out, which is tan theta. So what we find out from that is v squared over r is equal to g tangent theta. I want to get speed, so I'm going to multiply both sides by r, and I'm going to get v. Then I'm going to take the square root. So v is going to equal the square root of r g tan theta. And a lot of times students will get to this point and they'll be very excited because they've done all of this hard work and done it correctly, and they're happy and they think they've finished. They neglect to notice that r is not one of the allowed constants. You have to be cautious about that. When they say in terms of something, you have to wipe out and get it only in those terms. There can't be additional stuff. There can be additional constants. If you need a pi in there or something like that, you can get away with that. But there can't be a variable such as an r that would relate to the situation that's not included. But there's a little trick here. This is r. So while if you wrote v equals the square root of rg tan theta, you're close. You're not going to get 100%. All you really have to recognize is this is a right triangle. This is theta, this is the hypotenuse. That's the opposite side. So relative to theta, sine of theta is going to equal opposite r divided by hypotenuse, or L. Or another way of saying that is that the opposite side, r, is going to equal L sine theta. So I don't need r in my final answer, because I can say v, which is equal to r, is actually square root of L sine theta times g times tangent of theta. And now I have the speed in terms of only LG and theta.